In the previous video, we introduced the idea of an electrochemical cell, and we introduced some notation using an example of a reaction between zinc ions, silver ions, and silver. And we denoted that cell using this particular shorthand. This is the cell diagram for the cell that we designed. And I'll remind you that when we write it this way, electrons flow from left to right. All right, so they're going from the zinc to the silver ions and then creating silver metal. So what I want to do is look now at the forces of this. We're going to begin to link this to real thermodynamic quantities so that we can begin to understand the energetics of these particular kinds of processes. Now the first thing I'll note is that when we do set up an electrochemical cell like this, in terms of electrodynamics, the thing that is driving this is a change of voltage between one side and the other. So this delta V is not change in potential energy, for example, but it's a change in voltage. And we're going to essentially symbolize that as the voltage of the right-hand side minus the voltage of the left-hand side. And in general, for this to be spontaneous, we want this to be greater than zero. If it were equal to zero, there'd be no electron flow from one side to the other. Okay, what we have defined this as is a potential difference. That is how we would call this, delta V, and it represents the electromotive force. Okay, the electromotive force that drives the electrons from one side of the cell, from one half cell to the other. Now we often abbreviate electromotive force as EMF, all lowercase letters, interestingly. Okay, so when I say EMF, this is what I mean, is this potential difference or this voltage difference between the two sides. Now I will also indicate that this voltage difference is something that we can assign to a particular cell. And in fact what I'll do is write that as little e as the potential difference of the cell. And in effect, it's going to be equal to the voltage difference when there is no current moving. So I'll say this is in the condition of no current moving. So we're going to measure what that potential difference is. Now, you can think of this as being something like a balance point for that electrochemical cell. And in that sense, it is not too dissimilar from the sort of conditions that we placed on delta G when we talked about reactions. They reach a balance point that represents chemical equilibrium. So we're going to set up the cell so that it's at one of those balance points, but we can measure the potential difference between the two sides. Now the other thing I'll note is that for this to move, we've indicated that this potential difference has to be greater than zero. But we know that for a spontaneous chemical reaction, we must have delta G less than zero. So in other words, in the relationship between delta G and the the electric potential of this cell, there's going to have to be a minus sign somewhere to convert something that inherently has to be positive to be spontaneous to something that has to be negative to be spontaneous. And we'll see where that comes in just a moment. Now I want to make a brief aside to talk about units because those are going to be very important here. And these potential differences for the cell are measured in units of volts. But a volt is simply 1 joule per coulomb. And a coulomb is a measure of charge. Okay, just to give you an idea, one electron has a charge of 1.6022 times 10 to the minus 19 coulombs. So it doesn't have a whole lot of charge. All right, since one electron is maybe a little bit too small for us to measure in any sort of meaningful way, we're going to be more interested in what is the charge of a mole of electrons. So 1 mole of electrons would simply be Avogadro's number times this, and that will have a charge of 96,485 coulombs. And in fact, we'll say that this is a number that we want to represent as called 1 F or Faraday, and it has units of coulombs, coulombs per mole. Okay, named after Michael Faraday, famous physicist of the 1800s. This 1800s was a great time to live if you wanted to put your name on different things in science. Okay, So this Faraday is going to be an important ingredient because we're going to want to measure how much charge moves across a wire, because once we do, we'll be able to relate it to the number of joules that are involved, and we can now relate those joules, if you will, to an energy of some sort. All right, so how do we do this? Well, in the case of electricity, we've got a potential, and we can convert that potential into energy or work by moving a certain number of coulombs across a voltage. So work in this case, and I'll call it work electric, is something that we can relate to the number of moles of electrons. I'll call that Z. Okay, sometimes this is called N, so be aware that other texts may use N in place of Z, times the number of Faradays, which is the number of coulombs per mole, times the potential difference for the cell. Okay, so this will define the work that can be performed by the cell in electric terms. But now I want to touch base with thermodynamics, because back in lesson 3C, I know that was a long time ago, but we talked about how the Helmholtz energy was related to the total reversible work. And if you were watching carefully, you may have noticed that Gibbs energy is also related to work, but Gibbs energy was related to negative the reversible non-PV work. And at the time, you may have dismissed that as saying, well, we're never going to have to worry about that because all we're talking about are gases. Well, now we're not talking about gases anymore. Now we're talking about non-PV work. So in fact, this Gibbs energy can be related directly to the negative of the electronic work, which means that we can write that Gibbs energy change for one of these electrochemical processes is negative Z times the Faraday constant times the potential difference of the cell. Okay, and so this is going to be a very important relationship for us because it allows us to connect Gibbs energy changes to changes that we can measure electrically using an electrochemical cell. All right, now I will remind you that there were some other relationships that we had derived already for Gibbs energy in this particular module. And perhaps the most important is that the Gibbs energy of a reaction could be written as the Gibbs energy for the reaction in a standard state or reference Gibbs energy plus RT log of the reaction quotient. And I'm going to specify that this reaction quotient is listed in terms of activities. Okay, so if I do that, then that means that we can write this this expression as RT log, and now I'm going to harken back to the A plus B goes to C plus D kind of reaction. I have the activity of A raised to its stoichiometric coefficient, the activity of D raised to its stoichiometric coefficient, A and B in the denominator. So we'll have that all there. So we know that this is going to be true for a chemical process, and these electrochemical reactions are chemical processes. So now I can relate this to this same expression. It's equal to negative Z times the Faraday constant times the potential difference of the cell. And when we reorganize this equation, we're going to get a more useful equation, because I'm going to identify this thing as being representative of the electrochemical potential, the electromotive force that we would get if we had all of our conditions in standard conditions. If we had all of our solutions at 1 molar and we had all our gases at 1 bar, then this would represent sort of a zero or a reference version of the cell. Now this actually I've got to multiply this by minus ZE. So this is E cell divided by minus Z times the Faraday constant, but I hope you get the idea. Okay, so what this means is if I take this relationship up here between Gibbs energy and the energy of the cell, I can rewrite this whole thing as minus ZF E cell equals minus ZF E cell 0 plus RT of log Q. Okay, so this is the thing that I want to rearrange, and when I divide through by minus ZF, I will end up with the equation E cell is equal to its reference value minus RT divided by Z times the Faraday constant log of the reaction quotient. And this equation is one that will be very useful for us. It's called the Nernst equation, after Walter Nernst. All right, so this Nernst equation is going to allow us now to regularly convert between something that we measure in an electrochemical cell and our reaction quotient, which is something that will have useful information for us about the state of a chemical reaction. Now, I should specify still further that this E cell, and I want to make this emphasis, is something that is the cell potential when we're in standard conditions. So not just any conditions, it's under standard conditions. So that means 298 Kelvin, 1 bar of pressure, 1 molal of solution concentration, and so forth. Okay, this particular set of constants here, most of these are constant. R and F are constants. T we often measure at 298, so we'll call that constant. This particular combination of RT over the Faraday is equal to 0.02568, and that will be in units of joules per coulomb or volts. Okay, so we'll have volts, volts, volts in that equation. All right, this is true only at 298 Kelvin, but most of the examples and problems that you'll need to think about will be at that temperature. So it's a useful number to know.